Welcome to Talk Tensors. If you're tuning in, you're likely looking for the signal in the noise of machine learning research. We take that stack of papers that define the field, the ones you know you should read, and we actually read them. We pull apart the methodology, we scrutinize the results, and we try to figure out why it all actually matters.
Precisely. We're here to do the heavy lifting so you can get back to your GPU clusters.
So today, we're not looking at some preprint that just dropped on Arcrea this morning. We're taking a step back to do a retrospective on a real classic. If you work in natural language processing, this paper is arguably your Genesis block. We are going back to late 2018 to cover BERT, pre-training of deep bidirectional transformers for language understanding.
Oh, absolutely. It really is the paper that ushered in the ImageNet moment for NLP. Came out of Google AI language, authored by Jacob Devlin, Mingwei Chang, Kenton Lee, and Christina Tutanova.
Okay, so before we get into the architecture, let's try to nail down the thesis. If we strip away the massive hype cycle that followed this paper's release, what was the core technical claim that Devlin and the team were actually making?
The thesis was that the state-of-the-art models of 2018 were leaving a massive amount of performance on the table. And it was because they were constrained by directionality. The authors argued that by designing a model that could look at both the left and the right context of a word at the same time and in all layers, you could create a pre-trained representation that would just fundamentally outperform everything else.
And they were right. I mean, it shattered the state of the art on 11 different NLP tasks. But to appreciate why that was such a difficult engineering feat, we need to look at the landscape in, 2017, early 2018? We were already in the era of pre-training, but the field was kind of divided.
Right. You essentially had two camps. First, you had your feature-based approaches. The poster child there was ELMo.
And ELMo used LSTMs. It also claimed to be bidirectional, and I think this is a point where people often get confused. Why wasn't ELMo considered deeply bidirectional?
It all comes down to how the layers interact.
Yeah.
ELMo was bidirectional, but it was shallow. It trained two completely independent LSTMs, one reading the text left to right, and a totally separate one reading right to left. Then at the very end, it just concatenated them, just mashed those two representations together.
So the two directions didn't interact deep inside the model.
Exactly. It's like two people reading a book from opposite ends and only comparing notes when they finish the chapter. They don't influence each other's understanding while they're reading. The left to right model has no idea what the right to left model is seeing until the very end.
Okay, that makes sense. So that's camp one. Camp two was the fine-tuning approach, and the big one there was the original OpenAI GPT.
Right, GPT was already using the transformer architecture, which is way more powerful and parallelizable than LSTMs, and it introduced the modern paradigm we still use today.
Yeah.
Train on a massive amount of text, then fine-tune for your specific task. But it had a fatal flaw for certain applications.
It was strictly left to right.
Correct. Every token could only attend to the tokens that came before it. The authors of BERT argued this is suboptimal for sentence-level tasks, but it's absolutely crippling for token-level tasks like question answering.
Because in question answering, the answer to a question often depends on context that appears after the word you're currently analyzing. If you've got blinders on just looking at the past, you miss half the signal.
Precisely. So the field was stuck in this dilemma. You could have the deep, powerful transformer architecture of GPT, but you had to wear blinders. Or you could use ELMo and see in both directions, but you were stuck with this shallow concatenation of LSTMs.
Enter BERT, bidirectional encoder representations from transformers. They wanted the deep transformer architecture and true bidirectionality. But this introduces a massive technical problem right away. If you just let a transformer look in both directions in a standard language model, what happens?
The model cheats. In a standard language model, your goal is to predict the next word. If you have full visibility of the whole sentence, well, the target word is sitting right there in the input. The model essentially sees itself and predicts the target with 100% accuracy. The loss goes to zero, and the model learns absolutely nothing about language.
It's a data leakage problem. So to stop the model from cheating, they couldn't use the standard predict the next word objective. They had to invent something else. And this is where the masked language model, the MLM, comes in.
This is the core innovation. It was inspired by the closed task from the 1950s. They decided that instead of predicting the next word, they would take the input sequence and just randomly mask out 15% of the tokens.
Essentially just hiding them from the model.
Right. And the model's job is to predict the original value of those masked words based on the context from all the other words around them, both to the left and to the right.
Now, The paper gets into some really specific implementation details about this 15% rule. They don't just replace every chosen word with a mask token. I think this nuance is often overlooked, but the authors claim it's crucial. Why complicate it?
It's all about distribution mismatch. If you replace every target word with mask during pre-training, the model sees that token everywhere. But when you actually deploy the model, when you fine-tune it for real work like sentiment analysis, the mask token never appears. The model might not know how to handle meaningful representations in those positions because it's only ever seen a blank space there.
Sure. So if a token is chosen to be masked 80% of the time, can you walk us through how that actually works?
Sure. So if a token is chosen to be masked 80% of the time, they do what you'd expect. They replace it with the mask token. But 10% of the time, they replace it with a completely random word from the vocabulary.
Just noise, like swapping a dog ran with the apple ran.
Exactly. And then the final 10% of the time, they just keep the original word unchanged.
I see. So let's break down the logic. The random word forces the model to actually look at the token, doesn't it?
Yes. If the model always saw mask, it could just learn to stop paying attention to the token embedding at that position. By injecting a random word, the model has to say, wait, does apple even make sense in the context of the blank barked? It forces the model to rely on the context to see the apple is wrong.
And the 10%, where they keep the original word?
That biases the representation toward the actual observed word. It's like a control group. It tells the model, hey, sometimes the input is correct, so don't just blindly predict something else.
I like to think of it as a really rigorous study guide. 80% of the time, you get a blank space you have to fill in. 10% of the time, the study guide gives you the wrong answer to trick you.
And that final 10% where the answer is provided correctly forces the model to verify. It can't just assume the input is wrong or missing. It forces it to maintain a distributional, contextual representation of every token, not just the hidden ones.
It keeps the model skeptical. It has to look at every single word and ask, does this actually belong here based on everything around it, rather than just skipping over the non-masked words?
Precisely. Now, that covers the token-level training. But BERT is designed to understand language structure, not just individual words. So they introduced a second pre-training task, next sentence prediction, or NSP.
This gets at the fact that a lot of downstream tasks like question answering or natural language inference, they aren't just about semantics. They're about the relationship between two different sentences.
Correct. The model needs to understand logical flow. Does sentence B logically follow sentence A, or are they completely unrelated?
How do they structure the training data for that?
It's a simple binary classification task. They feed the model two sentences, A and B. 50% of the time, B is the actual sentence that followed A in the original document. The label is next. The other 50% of the time, B is just a totally random sentence pulled from the corpus. The label becomes not next.
So the model has to learn semantic coherence. It has to figure out if the topic just jumped from baking cookies to nuclear fusion.
Right. And while it sounds simple, the ablation studies later in the paper show that removing this NSP task significantly hurt performance on inference tasks. It proved that sentence-level understanding is a distinct skill from word-level understanding.
Let's touch on the inputs really quick. To handle these sentence pairs, they did some clever things with the embeddings.
Yeah, the input representation for any given token is the sum of three separate embeddings. You have the token embedding from the word piece vocabulary of 30,000 tokens. You have the position embedding, where it sits in the sequence, and uniquely, the segment embedding.
And the segment embedding is basically a flag for this is sentence A or this is sentence B.
Exactly. They also use special tokens. CLS is added to the start of every sequence. The final hidden state of that specific token is then used as the aggregate representation for the entire sequence in classification tasks.
And
Set P is used to separate the sentences.
Scale was also a huge factor here. I mean, this wasn't trained on a laptop.
Not even close. They trained on the BooksCorpus, which is 800 million words, and English Wikipedia, another 2.5 billion words. For BERT Large, they used 16 cloud TPUs. That's 64 chips running for 4 days straight.
That computational cost is what bought them the one model to rule them all capability. This is really where that transfer learning revolution hit NLP. Unlike ELMo, where you had to heavily engineer specific architectures for each task, BERT promised a unified approach.
That's the practical genius of it. The architecture is constant. If you want to do paraphrase detection, you just pack the two sentences together, feed them in, and use the CLS token output for a binary classification.
And for question answering.
You feed in the question as sentence A and the paragraph as sentence B. Then you just learn 2 extra vectors to predict the start and end span of the answer text. You're fine-tuning all the parameters end to end, but the architectural change is tiny.
Okay, let's look at the scoreboard. The paper claims it shattered the state of the art. What did the numbers actually look like?
On the GLUB benchmark, that's the general language, understanding evaluation, BERT Large scored 80.5%. For context, the previous best, which was OpenAI GPT, was sitting at 72.8%.
An almost 8-point jump is massive in this field.
It's huge. And then looking at SQUAD, the Stanford question answering dataset.
That's where the bidirectionality should really shine.
And it did. BERT Large got an F1 score of 93.2. That outperformed the human baseline on the leaderboard.
It was effectively reading and extracting answers better than a human annotator.
On that specific dataset, yes. It also just destroyed the competition on the SWAG dataset for common sense inference, beating the previous elite baseline by over 27%.
These are not incremental gains. This is a paradigm shift. But being good scientists, the authors did ablation studies. They dismantled their own model to see what was actually driving this performance, what was the most critical finding there.
I think the most validating finding was on directionality. They trained a version of BERT that was restricted to left to right, similar to GPT. The performance just collapsed, especially on SQUAD. It proved empirically that for tasks needing context from both sides, deep bidirectionality is strictly more powerful.
There was also an interesting note on model size. Usually we worry about overfitting if we use a massive model on a tiny data set.
Right, but they found that increasing the model size, more layers, larger hidden states, led to strict accuracy improvements even on very small data sets. This was counterintuitive at the time, but it really paved the way for the scaling laws we rely on today. If you have enough pre-training, extreme scaling helps even small downstream tasks.
So summing up the legacy, BERT marked the moment NLP became a full-fledged transfer learning field. You learn the structure of language once at great cost, and then you transfer it cheaply.
It established the transformer encoder as the default starting point for understanding text. I mean, while generative models like GPT-4 have the spotlight now, for pure understanding, for classification and embedding tasks, BERT-style architectures are still the bedrock.
It's infrastructure at this point. Which brings us to our final segment. We've analyzed the paper, we've respected the math. Now let's get a little speculative.
It is time for novel notions.
And as always, these ideas are for entertainment purposes only. Do not cite us in your PhD thesis unless you want your advisor to question your life choices.
But if you do run the experiments, we accept co-authorship.
All right, idea number 1, the temporal masking engine. We take BERT's masking methodology, but we apply it to human history.
History as a sequence.
Exactly. BERT learns context by masking a word to see if it can predict it from the surrounding sentence. What if we treat a timeline of civilization as the sequence? The tokens are major events. Invention of the printing press, fall of Rome, signing of the Magna Carta.
I see where you're going. You mask a specific event, let's say the Industrial Revolution, and you force the model to predict it based on the geopolitical context of the 1700s. That's the left context, and the societal outcomes of the 1900s. The right context.
And you use the next sentence prediction objective to model causality. Sentence A is a specific policy decision. Sentence B is the societal outcome 50 years later. Is next or not next?
So you're building a causality engine. If you could encode the data, which is a massive challenge in itself, you could theoretically use this to simulation test policy. You mask the current year, input our current geopolitical tokens, and ask the model to fill in the blank based on 5,000 years of training data.
It's basically Asimov's psychohistory powered by masked language modeling.
It's wildly ambitious, but the architecture, logically it supports it. Sequence transduction is sequence transduction, whether it's words or wars.
Okay, idea number 2. Let's move from history to biology. BioBERT for protein folding anomalies.
We've seen models like AlphaFold, but how does BERT specifically fit in here?
Well, the core argument of BERT is that left to right is insufficient because context comes from both directions. In protein folding, direction is 3D space. The end of an amino acid chain might fold over and touch the beginning. The interactions are physically bidirectional.
That's true. A chemical interaction can effectively skip the linear sequence.
So we treat a DNA sequence as the language. But we use that 15% masking rule aggressively. We intentionally delete or mask crucial functional parts of a virus's genetic code in a simulation.
So you're simulating a mutation.
Yes, but we use the BERT objective to predict the restoration. We ask the model, what amino acid needs to go here to make this virus functional again?
That is terrifyingly brilliant. By doing that, you're not just predicting the original virus, you are potentially predicting the next mutation that restores function after, say, a drug attacks it. You could anticipate viral strains before they even exist in nature by forcing the model to solve the closed task on the viral genome.
Exactly. We stop playing catch-up with biology and we start predicting the masked future.
It's a fascinating application of the denoising concept. You're essentially treating evolution as a noise reduction process and training BERT to solve it.
And whether you're predicting the fall of empires or the next supervirus, it all comes back to that core insight from 2018. Looking at the world, or the sentence, with both eyes open is just better than one.
Deep bidirectionality. It seems obvious now, but it took Devlin and his team to show us how to actually train it.
The paper is BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding. The link is in the description. Read it. It's a classic for a reason.
And just remember, 80% of the time read the paper, 10% of the time read a random paper, and 10% of the time. Well, keep listening to Talk Tensors.
Thanks for joining us on this deep dive. We'll see you next time.